Unit 8, our last of our core quizzes. And so you've learned a little bit of an introduction to inference in Unit 7, and now we're going to finalize all those topics. So if anything didn't quite fit yet in Unit 7, usually students tell me, especially Module 17, just kind of let that be in the background, kind of an idea of what we're doing, and now we're going to finalize it, and this is the version that you're expected to know. So in Module 19, which is what we'll cover in this video, we are going to be finalizing that confidence interval method. Unit 7 does have a Canvas checkpoint quiz, but doesn't at all have a mastery quiz. So again, even if you're finished with that already, don't worry about all of the ways we presented that. Really quickly, our course actually has the word probability in its title, and there's a lot of different probability topics, a lot of different ways to introduce and be explained them, and often it's a very difficult topic. And so when we made this material, we decided to focus on probability methods that are intertwined with the inference. And so really that came down to sampling. There are ways to just study probability by itself. So we kind of put two difficult topics together so we could get them out of the way, because they are part of the required material of this course. But you can see that they're in a unit that I am not focusing on as much, and so you can kind of get the idea of the long-term value of that unit. Okay, so let's go ahead and go on to Module 19 here. So we've been working with proportions, right? Proportions are percentages, and specifically we're trying to do this idea of estimating a population proportion. So you've been introduced to confidence intervals, and we are going to expand on that idea. So we'll take some notes here, recap the formulas we've seen, and introduce kind of the new final versions. Right? What is the purpose of a confidence interval? That's the title of the section here. Right now we're focusing on proportions. The next topic will focus on means. And means are the way we study quantitative data, and proportions are the way we study categorical data. And so that gives us the two main types of data we study before we get more complicated with multiple variables and multiple options. So what is the purpose of a confidence interval? To estimate a population value, which we call parameter, so to estimate a parameter. Those type of words you don't directly I'm not too worried if you learn that specific vocab word. So we have some ideas here. When would we need to estimate them? So what is the average amount of money that community college students receive in financial aid? Do the majority of community college students qualify for federal student loans? What proportion of community college students qualify for the BOG fee waiver? That used to be what is now called like a promise grant, I believe. It's a few years old and it's switched right after. So what is the average amount of money? We don't know that, and it's asking for a parameter. So yes, we would need a confidence interval for that. It's not the kind we're doing right now. That's an average, so that's quantitative data, but it is a confidence interval still. Do the majority? So it's like a yes-no answer, right? The answer isn't a number that we would best use an interval to describe. What proportion of California community college students qualify for the fee waiver? We look like we want a number, and we probably need to go out and take a sample to do it, just like the other one. Maybe someone's database has the right answer, which means we wouldn't need a confidence interval, but that sounds difficult to do. So then we take a sample, we use that to get a point estimate, but then we've discussed how it's better to have an interval instead. Right, so the formula we've seen, we saw it before in a simplified version that was only a 95% confidence interval, right? And so the 95% was why it had exactly 2 standard deviations, right? From our normal curve, 2 standard deviations is 95% of the data. And this time the data is essentially all of the possible samples. So in general, we have that more general idea, the sample proportion plus or minus the margin of error. So this whole calculation here is the margin of error. We've already had these comments come up in Module 18. So P is in there, but P represents the actual population proportion. It would be hard to do a confidence interval to estimate the answer already. So one thing we did is we said we used a previous estimate. And that might have helped us figure out, if we think it hasn't changed much, but we still want it to be pretty accurate, we can use a previous estimate. Right, margin of error and standard error. Right, so what does standard error tell us? It's the standard deviation of the samples. Right, and I think I already said this. Why is the margin of error twice the standard error? So, a long time ago, we've been really trying to introduce this idea of a typical interval. And so why is the margin of error twice? A typical interval, if you had normally distributed data, which is very common, and it turns out when we sample, it happens naturally. And so why is the margin of error twice the standard error? Because we specifically wanted the 95% confidence interval. So 95% and the opposite number to that, 5%, show up as very common probabilities. I think it's because both mathematically, they show up naturally. 2 standard deviations is 95% when we round. And 95% is a very natural high probability, with the other one being 99%. And so they are 2 very common ones we use. So I think it's both natural and just part of the math and how it worked out. We did have some conditions, so we do have to be careful, right? We need to know that the sample sizes are enough, which is what those formulas n times p and n times 1 minus p mean. We needed to know that it was random. Our sample was obtained randomly. So we had a few conditions, but those are always going to work in the problems we give you. We might ask you to check them. If you were doing this in reality, you would want to very carefully check the conditions. We're more focused on interpreting them in this course and the purpose of these problems. Okay, so the chair, so an evaluation of an academic counseling services on campus. All of your professors and counselors and different people on campus go through evaluation procedures. So the chair of the counseling department randomly selects 100 students and emails them a survey. 65 responded, 12 rated their counseling experience as unsatisfactory. Right, and so we're going to use this to estimate the proportion of the entire student body that has had unsatisfactory academic counseling. Hopefully your experiences with counselors have been reasonable. So we don't have a previous estimate, and so the first thing we did, we had said previous estimate, and then we were able to say after that, if we don't know a previous estimate, we can go ahead and use the sample proportion. So maybe I should add that in. So previous estimate, oops, or then the sample proportion. Right, so any symbol that has a hat on it represents in some way that it came from a sample. Slightly different types of hats, but that'll be somewhat common throughout. So it turns out that it is reasonable to just use the sample proportion. There's actually a lot of theory behind that, which we don't go into too much. If you decide you really like this topic and you want to be not even a math major, but a statistics major, um, some math majors maybe learn it. Also, um, you can take these classes again where you've also already taken calculus, and you can explain a little bit more theory, math-wise, how come some of these things work out like they do. For example, there's a very simple one of how come in our standard deviation formula a long time ago, there was an n minus 1 in the denominator. Okay, so let's go ahead and calculate some things just to remind us. So p hat should be a sample proportion. So it's the 12 people out of 65 who responded unsatisfactory. So 0.185 when rounding. So 18.5%. One decimal place is probably accurate enough here. Whole numbers will be okay, but now that we're doing a lot of calculations with them, I think you might want to do one decimal place. Okay, so now we have to verify the conditions work. And the main conditions are those n times p and n times 1 minus p. So we're going to calculate them, and we need to make sure each of those are larger than 10. But if we don't have p throughout, we can go ahead and use p hat. Turns out for proportions, anytime that they're in a formula, they're a good substitute. That won't quite be true in the next unit. Something similar will be true though. Right, so our sample size, so I wouldn't call it a trick question, but 100 is not relevant for the numbers here. 65 people answered the survey. If you're really studying surveys, you want to calculate your response rate, but that's not a focus of this whole unit. This whole unit is on the confidence interval and its specific interpretation. So that one is there for context, but we won't be using that. So n is 65, and p was 0.185. If you think of p hat as the fraction 12 over 65, if you multiply this, you get exactly 12. So one thing that these represent is just how many people say yes and no, and they each need to be larger than 10. Or in a way, how many people you predict are going to say yes and no. It's a similar idea. So as long as essentially 10 people are answering both yes and both no. So what we can't have is a scenario where we expect almost everyone to answer the same thing. Then our proportion methods won't work very well. And there's some ways around that if you really had to, which is not covered in this course. All right, so again, we have 65 now times 1 minus 0.185. So these will be all the people who said the opposite answer here. But by yes, I meant said yes, it was unsatisfactory. And so no, it's going to be something besides unsatisfactory. So that's going to essentially be all the rest. You can calculate it. Depending on how you rounded your decimals, you might get slightly different answers, or how many decimal places, but it's essentially going to be the opposite amount of people, so 53. Okay, so these are each larger than 10. If this question comes up on a unit, on a mastery quiz, I will clarify that I'm asking you to test the conditions. And otherwise you should do it, but I probably won't enforce that too much. Okay, so let's go ahead and get the confidence interval, the most important thing we're looking for here. So our p hat is 0.185 plus or minus 2 times 0.185 times 1 minus 0.185. Our sample size we're dividing by is 65. I recommend finding a calculator that you can type this all in very easily, and now you can start using StatCrunch for this. So in StatCrunch, you're going to go to Stat. Um, it's not a graph. We only really use two of those menu screens. And now we're studying proportions, and then there will be a confidence interval option when you get to there. Okay, so 0.185 minus. I do like doing these ones by hand to start. I think it makes it a little more clear what we're doing. But throughout the rest of the class, and at any point you want to, you can switch to StatCrunch. The old school TI-83 or 4 is probably more popular now. TI-84 calculators also have it, so you can use those if you'd like. They have a menu way to calculate these also. Okay, so 0.089 is when I subtract for the bottom one. I think I've mentioned this before. I like to use the Desmos scientific calculator. And the top is the larger bound, the upper bound, 0.281. So this is 8.9% to 28.1%. So this is the range of what we expect the population proportion to be, with a confidence of 95% for the context. And so let's put that in context. We are 95% confident that between 8.9% to 28.1% of students have had an unsatisfactory academic counseling experience. Would rate their counseling experience as unsatisfactory, something like that, just the context of the problem. That between 8.9 and 28.1% of students feel their counseling experience was unsatisfactory. Right, and so this is what you started in Module 18, and now we are kind of finalizing all of these versions here. It's very similar. And so we have our one last main thing to add to it. This sentence is kind of copy-pastable. We are X% confident. We're going to start changing that between the lower bound and the upper bound, percentages, whatever the context of the problem. You will for sure have to do this on the unit mastery quiz. Okay, so I don't think I'm going to calculate this one, but we can think about it really quick. And if you have your calculator handy, and especially if you haven't cleared out your work, you can very easily calculate it. So maybe I will. I still have mine handy. 95% are most common. It's the default for research, for media, you can see in there. But what if we changed it to 99.7%? What is it that changes? So we want to be more confident. It's very, you have to get used to the fact that that does not mean that the interval is going to get smaller. That would be great. But the way we can make this more confident without more data is to use a wider interval. Think about our typical intervals from before. They've gotten a little wider in a sense now because there's 2 standard deviations, not just 1. Along the way, we also took samples that made everything a little weirder. But now we can change this, how many standard deviations. Why is it 2, maybe instead of 3 or something? Because we wanted 95%. So if we calculated the 99.7, what would change? The 2 would become a 3. And so you would have the 0.185, but this is a 3 instead. Okay, the same info for above. I wanted to kind of simplify this a little bit. And so your margin of error is always going to be larger because it has a larger number multiplying in there. So this will always widen the interval. So 0.41 up through 0. No, sorry, 0.041, 4.1%. Up through 0.329, so 4.1% to 32.9%. So this widened the interval, we gave it more air. Because we're allowing ourselves more air, we are more confident. The margin of error number, the standard error is always the same, it's just that square root calculation, because that's a single standard deviation. The margin of error is what you allow to change depending on how accurate you want to be. And so we made it wider because now we're more confident. Right, like if I asked you in a class that has maybe normal exams and you get out of 90, you get out of 100 on it, and you get a 90 or an 80 or a 70 or something like that. If I asked you, how'd you do? You'd be like, well, maybe I got around an 80. And you're like, okay, but I need you to be more confident about your answer. You're like, okay, well, I probably got between 70 and 90. I answered a lot of the questions, but I don't think I got everything right. It's like, I want you to be even more confident. So instead of 70 to 90, you might say, well, I got between 50 and 100. For sure, got, between 50 and 100. So widening the interval allows you to be more confident. So those are some ideas on why that makes sense. Okay, nobody uses a 99.7% confidence interval, even though that's a nice whole number amount of standard deviations, just because we also obsess a little bit in statistics of nice round numbers. 99.7 we don't consider a round number, but 99% we will. It feels more natural. So we're not going to go through and calculate it too much. Here's different cuts up of the standard deviation of the normal distribution probabilities. But we'll go and summarize it here for you. So so this is the final formula. If you did pick up the printed notes, this is one of the first pages for sure, especially towards the end here with our end material that you want to bookmark. I have 2 pages that I think are important for confidence intervals. This is one of them. We'll have one for our slightly new topic called hypothesis tests. Okay, so confidence level, 68%, we would have a z-score, which just means the amount of standard deviations of 1. That's not very common. We want to be more confident than that, and just because it's a nice round number, we don't really use it. But it's true, but we don't use it. So it's not wrong or anything. All of the rest of the next 3 are all used. The last one is also not used, even though it's a nice whole number of 3. Calculators are doing this for us in reality, so it's not a big deal. 95% is still used and has that nice round number of 2. Technically, it's not 2. It's been rounded a little bit. The z-score is 1.96. But 2 is fine as an estimate in our class. And so the other 2 are, if you want to be 90% confident, how many standard deviations away from the mean cover 90% in the middle? 1.645. If you want to be 99% confident, so a little wider, how many standard deviations, what's the z-score of how far away you need to be? 2.576. And so these are the 3 common, again, 99.7 is not actually common. So you should expect on checkpoints and the mastery quiz to have one of these 3s to use there. Okay, so we'll do at least one problem here. You can check if that link still works. So Gallup used random digit dialing. That's the way they actually get their sample. And they asked 450 people in the samples below. So the whole thing is about confidence in institutions. It's a weird example of the word confidence, not statistically, just the normal word confidence, like in English. Okay, so America's confidence in the U.S. military, the institution with the highest confidence rating in June 2012, says 75%, is down only 7% from being at an all-time high of 85% in 2003. So we're going to calculate a 90% confidence interval for 2003 and a 90% confidence interval for 2012. So these are the two ones that we want to use. And again, you can now switch to StatCrunch and do that. You can calculate these by hand. Both are, it's a little quicker on StatCrunch. StatCrunch asks you, though, how many people and the total, instead of our formulas having p hat. So whichever one you'd like to get used to. In our later units, we're going to kind of have to use StatCrunch because the calculation gets too difficult by hand. This one does not. So right now it's fine either way. If the calculation by hand makes it a little more reasonable, feel free to stick with that. Okay, so first we're going to do 2003 one. And so the 2003 number is that 85% of people felt confident in the U.S. military. Right, so what did that technically mean? Just to clarify, they reported a great deal or quite a lot of confidence in the U.S. military. Okay, so for 90% confidence, our critical z-score is what it's officially called. That's why it has a little z, sorry, a little c. Z for z-score, C for critical. But it's how many standard deviations you need so that the middle percentage is that one we're looking for. So a lot of this, topic goes back to Module 12 in Unit 5 about the normal distribution. Okay, so it used to be 85%. Our z-score is 1.645. We could either use the previous estimate. The 2003 number is the oldest one, so it might be the previous estimate. But you can go ahead and from now on just use the current one. I think that's the more common day-to-day calculation for this anyways. So I'm going to put 85% here, p hat times 1 minus p hat, 0.85. And our sample size this whole time was 450. Okay, so type that all in, get a value for there. So 0.85, 1.645, and then the square root. Right, so the lower bound is 0.822, and the upper bound is 0.878 when rounding, 878. Right, so that's percentages are probably more reasonable, so 82.2% up to 87.8%. Right, so 85 was the number, but that only came from 450 people, and this is supposed to be about all American, probably, adults. It's almost always adults. Kids don't get surveyed. We leave them alone, but almost all surveys are geared towards adults. So somewhere between here, we are 90% confident that that's the true number for all the millions of Americans. That's the idea. Okay, and let's do that number for 2012 instead. So everything's very similar. They were still 450 people in the survey. Right, so in real life, they probably kept on calling until that 450 450th person answered. So that had gone down to 75%. It says it's gone down 7%. That must be a typo. Guess we can't do the math there. So 75% is our new p-hat. Our sample size is still the same. So plus and minus 1.645 instead of 2, which means it's going to be a little narrower, because maybe this number is just maybe not as important. And so usually if something's not super stressfully important, pick a 90% confidence interval. If you just want to be normal, pick 95. If it's really important, like medical scenarios or something like that, pick 99, so that that range is widest, which is kind of like the worst case scenario, because you're extra confident. All right, p-hat is 0.75. 1 minus p-hat divided by 450. Well, I'm just going to go in and change everything. You're almost always on your computer probably in this class. Go ahead and use, like, I use Desmos Scientific Calculator. Type the whole thing in and just press enter once as best you can. It means it's quick to go back and change things in case we ask questions like this, which are somewhat frequent. No matter what, you have to switch the plus to a minus. So I type the whole thing in and just press enter once. Also, it actually helps guarantee that you make less mistakes doing it like that. Right, so the bottom of our interval is 0.716. That's less than 0.75, so it sounds reasonable. And then 0.784, 0.784 is the top. So 71.6% to 78.4%. Okay, so those are our two intervals. We need to think about, like, what's the purpose of the intervals and how do we use them. So an interval, the best way to use it is the thing I'm thinking in the interval or not? We are saying that the population value is going to be in this interval. It could occur anywhere. That's not something we know. But so it's from about 71 to 78, I guess 72 when you round, in 2012. It's a long time ago now. There might be a new survey out. It used to be somewhere between about 82 and 88 when rounding. Those intervals don't even overlap. So this is a common thing we can do with intervals. It's all about is it in or not? But if we have two, we can think about them as did they overlap. These two don't even overlap. So in kind of the lowest case scenario for 2003, doesn't match up with the largest possible proportion of 78.4 in 2012. And so we are really sure that these are different. And that is an idea of how useful or important this new material is. We can say we're kind of at this 90% confidence level that we're really sure that this number has actually gone down. Right? If someone polls and they're a politician and they go from 80% or more realistically, let's say 55% down to 52% polling numbers, is that really going down? It's a little lower, but everything is random all the time. We don't exactly know who we're going to get answering the phone. This scenario, it has changed enough that we think something is different. Okay, so the intervals don't overlap. Is it the same? No, they don't overlap. That is one way we can use these. Just a reminder, what does that 90% confident mean? So you've seen some scenarios of this in some simulations. 90% confident means in the long run, it's the chances that your interval works. So in the long run, the chances the interval works. It's not quite the chance that your interval is accurate right now because we only took one sample and we either got it right or we didn't. and so there isn't really a probability associated with that. That is very technical. We won't really want to have you worry about that too much, but just know that what we're not saying with a confidence interval is that it's a pure probability. It's a little bit different than a pure probability like rolling a dice. So it's not that level of probability. Okay, we'll read through the next one, and I'm just going to point it out. So we're kind of giving you some of the StatCrunch examples. Okay, sorry, this went on 2 pages. So same survey, church or organized religion has lost 24 percentage points, with 44% of those surveyed reporting a great deal or quite a lot of confidence in the church in 2012. So it used to be 68% in 1975. That's a lot longer back. Okay, so in the StatCrunch menu, it's one sample. We're just taking one sample. You go to Stat, and then Proportion, and then you pick one sample. It's pretty straightforward to see that on StatCrunch. Just go to those menu screens. We don't really have a lot of things we do, especially right now. So the one difference in StatCrunch is that you have to tell it how many actual people out of the total. If, like in these problems, you're given the percent, you just have to multiply that back by the total. So we were told 44%, so you'd multiply, to get this 198, you'd multiply 44% by 450. That's how we got that number. You can round to the nearest whole number. But this sample proportion is the more common one to give. Some calculators out there do that, so feel free to swap which calculator you use. On anything not timed, or not just timed, but anything take home, feel free to use them. And then on the interview quizzes, you can just pull up the one that you're more familiar with. Okay, so standard error, that'd be the square root calculation. It doesn't give us exactly the margin of error. And then we have the lower and upper limits. Okay, so one of these is the calculated 90% confidence interval, and one of them is the calculated 99% confidence interval. In addition to introducing StatCrunch, we want you to see the difference in these two intervals. So this will be 40.2% when we round, 47.8%, the upper limit. This is 37, it's going to be 38. When we round, and then 50. Alright, so which one is which? We were saying earlier that if you had a 99% confidence interval, your critical z-score, your amount of standard deviations, is larger than the 90%, and so the interval that is wider. So the 90% one should be the wider one. Which one is wider? These have the same sample proportion, so they'll be centered at the same spot. So we're just looking for one that's wider, and so this one here is wider. So this is the 99% one, and this is the 90% one. Right? You probably, if you had been doing this on your own, or if you paused, you would have found that out by which has the largest margin of error. Right? That's the 99%. I kind of already explained that. And which interval is most likely to contain the true value. So a wider interval is more likely to work. That is the design of it on purpose. We widen it. We know how accurate it is depending on the z-score number, the amount of standard deviations. But we widen it, it's more accurate now. Again, if I'm asking about your grades, you say, I don't know, maybe I scored around an 80. But if I say I scored between 50 and 100, you're much more confident about that. If you thought you scored around 80, you're much more confident you scored between 50 and 100. So widening it makes you more confident. Which one is best? So now these are personal opinions. So this is a different one. Is this situation important? Maybe it depends who you are, or the context and how you're using these. And so that's up to you. 95% is the most common one in actual research and the media. And here's a different question. What could they do to decrease the margin of error? So let's say you want to be 99% accurate. You know you're going to come into this question and you're going to want to be 99%. How can they do that? The only thing they can do is increase the sample size. So a lot of real life polls have sample sizes about in the low hundreds. 300, 400 is going to be about the smallest. Otherwise, your margins there are just too large. And they go up to a few thousand. We don't really have them go much further than that because then our confidence intervals get really small. In real life, that's a lot of data to collect also. It can be very expensive. And at that point, we're just getting numbers very close to the population value anyway. We're asking, we don't usually take a survey of 100,000 people. So one, maybe 2,000. So those are the real life answers and how much we do there. Okay, so that is all of Module 19. Module 20 is an introduction to the absolute most important topic in our course, hypothesis testing. So slow down for this one if you need. Don't worry about being maybe perfectly on time for Module 20. 20 and 21, we really focus on hypothesis testing. I'm going to give you some additional topics that don't directly show up here in the notes and don't show up on Canvas and how to think about this. So I'll see you in Module 20. Module 19 there was the final version of our confidence interval, and now we're going to introduce and finalize hypothesis testing in Module 20 and 21. We really slightly introduced it in Module 18, but it was very subtle, and now we're going to come and fully introduce that. All right, I'll see you in Module 20.